Fantastic, fantastic. Okay, buenos días a todos. Good morning. We are honored to have today Professor Yury Gogotsi, who is participating in this ICMM seminars. Professor Gogotsi is a distinguished university professor in the Department of Material Science and Engineering at Drexel University in Pennsylvania in USA. And he is also director of the Drexel Nanomaterials Institute. A Master in Science in 1984, PhD in 1986 from Kiev Polytechnic University, and he's also Doctor in Science from the National Academy of Science of Ukraine in 1995. He made excellent contribution on materials for electrochemical capacitors and other energy storage devices, and studies on surface modification and purification of nanotubes and nanodiamonds, and also studies on, for instance, water inside the nanotubes and so on. But we can be sure that his main contribution at this moment has been the discovery of MXenes, to which Professor Gogotsi will dedicate today's lecture. He is recognized as a highly cited researcher in material science and chemistry with more than 200,000 citations, an age index of 201, at least yesterday. And this is increasing. He has received numerous awards for his research, including the Ceramic Prize from the World Academy of Ceramics, the Materials Research Society Medal, the American Chemical Society Award in the Chemistry of Materials, etc. He has been elected a Fellow of the National Academy of Inventors, the World Academy of Ceramics, the European Academy of Science, and many professional societies. He holds honorary doctorates from several European universities. So, and the talk of today is the two-dimensional carbides and nitrides, MXenes, the building blocks for advanced technology.
Eduardo, thank you very much for your kind introduction. Thank you very much for inviting me to speak. This is my first visit to your institute, even though I'm familiar with some of the research done nowadays, but also, of course, the work Eduardo and his students, postdocs, did a couple of decades ago, laid the ground for much of two-dimensional assembled materials, nanocomposites research, which is going on nowadays here. I'm going to talk about MXenes, even so after listening to the MXene song, you don't need my lecture, you have probably learned everything you need really to know about MXenes. And this song was written by Marcello Andrade, who was a master student from European MESC program in my group. And it was recorded when he already started his PhD at University of Nantes with Professor Thierry Bruce. And this was actually my present last summer when I came to speak at the summer school on energy storage in Nantes. This was a surprise song for me. But if you enjoyed it, you can just go to YouTube, type the MXene song, and you will find the song, and feel free to share and put likes on it here. And there will be another MXene song released soon, was written by my current postdoc. And I think if people write songs about MXenes, they're really excited about it here. And the key thing I want to achieve today with my lecture, get more people excited about this really wonderful class of materials with so many opportunities. And this will be the topic of my research. But what is also necessary to understand that MXenes are a new member of a two-dimensional materials family. And there are many two-dimensional materials here. And actually, I won't start with graphene. Truly, clays, oxides, were the materials with dielectric properties which have been studied for years. Clay is now probably the most widely used 2D material. It's like in bumper of every car, in composites, everywhere here. But clearly, discovery of interest in physics in graphene by Andrew Geim, Kostya Novoselov in 2004 attracted much more attention to this class of materials here. And I personally look at all two-dimensional materials, from clays and double hydroxides to oxides to dichalcogenides and graphene and boronitride and others, as building blocks, bricks, Lego stones for the future technology. When we can do both, we can assemble entire devices taking dielectric, semiconducting, and metallic materials. When we can assemble these two-dimensional sheets to create new materials, artificial assembled material with combination of properties no single material has. And of course, you can combine them with polymers, organic molecules. You can trap liquid in a solution and ions between the layers, intercalate them, and do lots of other things. So it looks really at these materials as building block of future technology. But why discovery of MXene in 2011, and this was a work published in Advanced Materials, and Michael Nagib, PhD student who worked with Michel Barzou, my colleague at Drexel, expert in max phases, and myself, was the first one to make and publish in 2011 the first MXene, titanium 3C2. What you see on the cover here are actually not single layers, those are multi-layers lamellas like in vermiculite clay or thermally expanded graphite here. But it brought truly metallic materials to this group, because graphene, being often praised for its conductivity, is not a metal. It's zero band gap semiconductor. It needs to be doped, or defects should be created to create carriers. Titanium 3C2, all other MXene in non-terminated state, are true metals with a high density of state at the Fermi level, high concentration of carriers. And this was actually what was missing in the family of 2D materials. Now we have kind of a complete set to build the future technology here. Now, let's look into chemistry of these materials in more detail. So what do we have? So M in MXene stands for one of those earlier transition metals, but you can also put lanthanides instead of one of the elements in the structure. X stand for carbon or nitrogen, can be substituted by oxygen. And at the end, you will see TX, because unless you make material in deep vacuum, your transition metal will never stay non-terminated. As soon as there is any environment, the metal will gladly give electrons to whoever wanna get the electrons and get oxygen, hydroxyl groups of its solution, halogens, chalcogens, and surface. But definitely the surface chemistry to a very large extent determines the properties, and we can get all halogens, chalcogens, oxygen, hydroxyl group, amino group, phosphorus, antimony. We predicted computationally arsenic is also possible. It's just a matter of going to make it here. And they come in 4 basic structures. This one we discovered with my students just a couple of years ago. So if you take 4 structures, a dozen of transition metal, carbon, nitrogen, a dozen of surface termination, you end up with about 1,000 simply of combinations of these elements that you can produce stoichiometric materials. Imagine, you can make 1,000 of new materials, but moreover, you can mix and match an X site making carbonitride or an M site making solid solution. So really, infinite number of new materials can be made in this system. Moreover, many of them can be made of common and abundant element, like, for example, titanium, carbides, nitrides, carbonitrides. Precursors we use for them, and I will talk about them for selective etching, like max phases, contain aluminum or silicon or titanium. We can make them using vapor phase synthesis from, again, very, very common materials. What does it practically mean? Those are materials not only for small volume catalytic or electronic applications. They can be used for large scale applications, thermal insulation, water desalination, filtration, gas separation, energy storage harvesting. And this is again very important. When you make material, for example, using rare elements, gold, platinum, or tellurium, which is as rare as platinum, doesn't matter how good your material is here. There is simply cost associated with it. Here, it's economy of scale. If you learn how to make it in large quantities and make in large quantities, they can become very inexpensive. So what do we have today? We have actually a very large family of materials, of which only about 50 basic structures, not counting surface terminations, have been reported. Couple of dozens of solid solution, as I mentioned, we can mix and match M element and actually make high entropy multi-elemental MXenes with up to 7 different transition metals. But we can also make even more complex structure, atomic sandwiches out of plain odorate MXene when one element, for example, chromium, is on the surface, another element, for example, titanium, is in the middle. The outer element will determine electrochemical, chemical, catalytic properties of the system. The inner layer will determine transport properties, electron transport, for example, here. We can make also in plain odorate MXene with alternating atomic columns of different metals. For example, yttrium and tungsten or moly. And if we etch one of them more active chemically, like yttrium or scandium, we will end up with materials with like atomically thin trenches of vacancies here. So I think you get the idea. We can really do nowadays atomistic engineering of two-dimensional materials. We have almost infinite number of composition in a variety of different structures created. And this is the beginning only. People make nowadays two-dimensional borides, silicides, more complex structure, and I'm sure more even further interesting arrangements of atomic paper. And don't forget about TX, the surface terminations. What is also very important, if you take a graphene and modify its surface, making graphene oxide with oxygen hydroxyl groups, or graphene, hydrogen covered, you kill the conductivity. It drops by 6-7 orders of magnitude. In this case, you can change surface chemistry and still keep material conducting, because the element of transition metal are there, they will provide conductivity. For some of the MXene, especially thinner layers, you can open the band gap, for example, by putting oxygen on the surface and pulling 2 electrons from each atom here. But for many of them, you can maintain conductivity. Naturally, with this huge number of materials, there is research going on all over the world. There are tens of thousands of people who co-authored papers. China is far ahead compared to other countries. There are definitely activities in Spain as well. And if you want to read about MXenes, I strongly recommend this special issue of CNN dedicated to MXene. It's a March 25th this year issue. It has a very nice article, cover story about MXene, which simply describe MXene from discovery to potential application, interviewing many scientists, including Michael Naguib, who is now a professor at Tulane, who made first materials here. And what is interesting, when we discovered MXene in 2010, we discovered it in 2010, but first paper was published in 2011. There was very little interest to these materials. There were already so many other materials, two-dimensional materials. Graphene just got a Nobel Prize, virtually at the time when we discovered first MXene in the lab, made it here. So for a few years, there were very, very few publications, like 4 years of first publication. Then they started to grow, and they started to grow from 2016, when we showed, for example, that MXene outperform all other known materials in electromagnetic interference shielding. and then a number of other properties. And you see it's quickly growing. This year was incomplete when this article was prepared. I know that already like a week or two ago when I checked, the number of publications this year was at the same level as in 2022, so it's probably will be there somewhere this year. But what is also interesting, we discovered MXene in the US. But you see now the proportion of papers coming from US shrank to a fairly small one. China is clearly the dominating force. But if you look at Europe, India, where was very little research up till a couple of years ago, Korea, they already have overtaken the US in the total number of publications things here. So research is going on clearly worldwide, and the research in Europe is also picking up here. Now, so you know now we have this enormously large family of materials where only very small percentage of materials have been produced already in the lab, about again maybe like 47, 48 basic structures plus a few dozens of solid solutions with a lot of opportunity for discovery. You can go back to your lab after my lecture and start making new materials never made before. They can be made of abundant elements. So how do they make them? Initially, Michael Nagib made them by putting titanium aluminum carbide into hydrofluoric acid, etching away aluminum from compound known as a max phase. So what are max phases? Those are layered carbides and nitrides of transition metal. When you look at the layer of transition metal, separated by a layer of so-known A element, aluminum, tin, gallium, silicon. These compounds were discovered by Novotny and others in Austria in 1960s, and my colleague at Drexel, Professor Michel Barzoum, is really a leader in the field who developed them into materials family. Things here. So these layers of carbide are actually strongly bonded. So titanium aluminum bond, for example, in this case is a strong intermetallic bond. You cannot shear and break it easily mechanically. So unlike graphite or moly disulfide or boron nitride, you cannot just simply mechanically easily exfoliate them. You have to etch. And we were able to etch this layer. Actually, we can etch it over tens of micrometers, removing monatomic layer of materials. What happens when you do it? Transition metal picks oxygen, hydroxyl group, fluorine, whatever else is in the solution, etching solution. And now there are weak van der Waals hydrogen bonds, water molecules with ions in between. And those materials can be delaminated, just like, for example, clay or graphene oxide, because surface chemistry is similar in this case here. Nowadays, we have many ways to make it here. We can still use for some of the MXene hydrofluoric acid, but for many others, we use other fluoride-containing acidic solutions. You can avoid using HF where limited in your lab, for example, using hydrochloric or sulfuric acid with lithium or sodium fluoride, forming some acid in situ. Can use electrochemical etching to have another way to control the rate of the process and differentiate applying electrochemical potential. Alkaline, hydrothermal, supercritical CO2. But what is also emerging in the recent years is etching that produces halogen. First of all, Lewis acid emulsion salt, but also gaseous etching using chlorine, HCl, others. You can also do it in solution. In this case, you can actually get uniform halogen terminated MXenes. And they have different properties because their surface is different. But moreover, when you have metal halogen bond, you can use very well-known organic chemistry techniques to graft various molecules on the surface. So you can develop hybrid materials, organic, inorganic materials, where organic molecules, moieties, covalently bonded to these metals that can inject electrons, opening another realm of opportunities, designing very interesting materials with potentially very unusual properties here. And last year, Dmitry Talapin's group from University of Chicago demonstrated CVD synthesis of materials, and then actually it was scaled up to vapor phase fluidized bed synthesis, which allows large volume of synthesis, like carbon nanotubes from titanium tetrachloride and methane. And we can also topochemically transform two-dimensional oxide, dichalcogenides, graphite, and so on. So basically, what we have now is a very large variety of synthesis methods. Depending on what your applications are, what kind of surface chemistry you want to have, you can select the message you need. Just a warning, not all of them have been shown to work uniformly for all max phases or gas phase synthesis of all MXenes. We're still starting to explore. Naturally, with such a huge number of materials, we need guidance from computational science. Which chemical bonds in max phases can be broken easier, but what kind of compounds? Everything from purely thermodynamic modeling, Gibbs energy minimization, to DFT calculation, to understanding with molecular dynamics, dynamics of transport between the layers, and so on here. But again, keep in mind, depending on the surface chemistry, even for nominally the same, say, titanium 3C2 MXene, you will get different properties. For example, these materials produced by wet chemical etching will be easily dispersible in water because they will be hydrophilic, and you can disperse them in water, forming stable colloidal solutions. And you see different MXenes will give you different colors because different optical, electronic properties. But halogen terminated MXenes will be hydrophobic. So again, you can control properties through synthesis of materials. Things here. We do our best to educate people how to make materials. We write papers. For example, this one is a June issue of Nature Protocols. This is a cover article of MXene. This like accordion-like structure after etching. It describes very much detail how make titanium 3C2 from max phases by, first of all, wet chemical etching. We had a recent review. We teach twice a year a 5-day course online, but there is still much, much more to do. But what is also important, many of this methods allow us to produce again a large amount of materials. Why I'm focusing on this? Because whenever you have materials made of abundant element and you can make in a process that intrinsically scalable, like wet chemical etching, you dump into reactor max phase powder. This reactor was designed by us by Materials Research Center, Ukraine. We get like 100 gram in a single batch produced titanium 3C2. We call it MXene clay because it has water and ion between the layers. So it rheologically, actually, after using lithium fluoride HCl etching, behaves like clay. And after that, you can disperse it, and you can see, for example, here about 150 liters of delaminated titanium carbide MXene in these 5-gallon containers standing things here. And this is my postdoc, John Wang. He's actually joining as a faculty University of Texas, Dallas in August. Is holding 1 kilogram of MXene, which was produced within 24 hours in our lab. So again, it opens opportunity for large-scale applications. So in this process, we start with ceramic powder. We dump it in solution, make it this MXene clay, and we disperse it in water, again, without any binder surfactants. So this is wet chemical method, and it has advantages because we get like a solution of colloidal solution, colloidal dispersion of two-dimensional particles in water with no surfactant needed, unlike say metal, ink, or graphene, and it's right away will be conducting. But if you want to make materials which is uniformly terminated by halogens, materials that can after that be much easier functionalized chemically, you may wish to use different methods. And the most developed one is the one which uses various type of chloride or bromide salt, usually in a mixture, where you can replace aluminum with, for example, zinc or other metal, which is easily etchable. And after that, you can remove this metal and get chlorine, bromine, iodine surface termination, and get a material with different properties. Moreover, working with Professor Qin Huang, who initiated this approach, and our collaborators in Sweden, we showed this is a very, very universal approach. We can take max phases use this Lewis acid molten salt as scissors to cut existing bonds and put any virtually metal element which in max phases won't be thermodynamically stable. You cannot make from elements or other sources a max phase with these elements because there is always another compound with lower Gibbs free energy. But you can put in the layers other elements designing layer structures, for example, gold or platinum or bismuth. And you can also completely remove them, making layers of vacancies, pretty much naked MXene. But after that, you can also put various surface termination on demand. Chalcogens, halogens, phosphorus, antimony. So basically, we can cut and paste elements into these layered structures. It's a little bit like a CRISPR. Editing DNA, we can edit layered ceramic materials today with this. Making either layered or 2D materials here. And actually, you can, just like about a month ago, there was a paper from Johanna Rosen and colleagues from Linköping University. They did differently. They removed layers of MX, leaving just gold layers. And this paper on Goldin, two-dimensional gold, has been making headlines in the past few weeks. Think here. But for us, what is important, we can create new materials with very different properties. For example, what you see here are materials which some of you may look at like dichalcogenide because there is tellurium or selenium on the surface. But in the middle, instead of a monatomic layer of transition metal, we have a layer of carbide. It's like a carbochalcogenide, a hybrid between dichalcogenide because the surface looks like surface of dichalcogenide, and in the middle you have a metal carbide. Or for the first time we put antimony. This was the first publication, antimony on the surface. So I think you get the idea. You can make a huge number of new materials. You can really design chemistry of two-dimensional materials nowadays. You're not limited by what is given to us by the nature. It's carbon or molybdisulfide or something else here. We can design with it. And there are many other ways. We showed also recently that we can make by gaseous etching, something we used to make carbide-derived carbon, removing just both metals, iodine and chlorine terminated materials, just without any washing, any water, because molten salt you have to remove by washing salt, sometimes changing termination and so on here. And of course, sky is the limit here. I'm referring again to a paper from a Linköping group doing this, predicting, this was published in Science in March, I believe, this year. They predicted, for example, silicides, two-dimensional silicide by selective etching and demonstrated on ruthenium silicide with oxygen termination here. Definitely many more materials in other inorganic transition metal systems can be made and discovered from layered structures by this type of a selective etching techniques here. Now, we have this infinity of materials. We can make them into solution or make powders. How to process them? What is very important? Whenever we produce this 2D or non-delaminated 2D from ceramics, depending on surface chemistry, we may have different properties. If we would use wet chemical etching, we always get material with negative charge on the surface. Remember, lots of electrons in this material. As a result, with zeta potential being below minus 30 millivolt, close to neutral pH, some of them goes to minus 80 millivolt, titanium carbonitride, we can disperse them in water without any additives. And that's again very, very important if you think about green processing, inks. You don't have binders and surfactants that you need to burn afterwards, and sometimes it can be very toxic here. You can just disperse material, and depending on particle size, for example, smaller particles will form at the same concentration much low viscous solution, 5 to 10 milligram per milliliter. In this ink we can use, for example, for inkjet printing, spray coating, deep coating, spin coating. But if we have a solution which is either containing these very large particles at smaller concentration or larger concentration of smaller particles, we can get a liquid crystalline solution. So flakes cannot freely rotate in solution anymore, and they get very well aligned when you can wanna draw fibers or make by doctor blading or screen printing patterns and films and so on, or do 3D printing with these materials in here. So again, it's just pure MXene with no additive. So you control viscosity and design colloids for processing and process from pure water with no additives, very important. And of course, chlorine terminated, for example, MXene will be different. It will be hydrophobic. So you will have to disperse it in non-aqueous solvent like THF, NMF. You can actually transfer it after that to isopropanol, but it's hydrophobic, it doesn't imbibe water. It has its own advantages, so you're looking for hydrophobic film, you again can do it. Things here. Now, it's great to have an infinite number potentially of new materials made from abundant precursors in a highly scalable processes here. Process them from pure water without anything added. But is it useful? If you can get the same properties with clay or graphene oxide or graphene, why really bother? Well, it's still interesting chemistry. But what is important? The key is, of course, to real application of materials is the property. So what is unusual that MXene bring to the table? One of them is high metallic electrical conductivity. As I mentioned, MXenes are conducting materials. We get just simply by drying the film more than 20,000 Siemens per centimeter, pushing to 30,000 nowadays in the lab. For people who don't know, for example, if you work with graphene, you make graphene oxide, you reduce it, you will get at maximum 2 to 4,000 Siemens per centimeter. We get 10 times more without any reduction process and without any post-treatment. So it's 10 times more conducting the reducing graphene oxide, and hydrophilic can be like graphene oxide. So it's a very unusual combination. You basically can make like a metallic clay or water dispersible metals. They're very strong. Actually, they are stronger than reducing graphene oxide or graphene oxide, and I'm compared to materials that are used in practical application, not ideal sheet of graphene. And these flakes are about 20 microns. You saw more of these flakes here. Those are flakes on a silicon wafer. The lighter ones are single layer flakes. I've never seen an oxide, hydroxide, dichalcogenide flakes produced from solution in that size. And simple is very easy. They will just break from thermal vibrations in solutions. But you can make it with MXenes. Those are all single layer flakes you see here, overlapping one, just an optical micrograph. So you can make very strong material, which again opens entire domain of application where strength microscope, ultra-thin membranes, coatings, devices, and others here. But they all come variety of colors. What it means variety of electronic and optical, optoelectronic properties, plasmonic, electrochromic here. And they're among the most efficient, almost 100% light to heat absorbers within their absorption band. Plus they have large electrochemical active surface, anything. But the key thing is here, all these properties are highly tunable. In other aspects, they look like other two-dimensional materials. Single crystals you see from high resolution TEM and selected area diffraction. They can be assembled into MXene paper, very similar to graphene paper, something else here. And actually those bulk properties measured on paper when you have hundreds, thousands of junctions between the flakes, still very high conductivity, and again, dispersible in water you have seen. Now, nanotechnology, nanoscience is not about making things small. It's first about controlling properties in nanoscale. And this is where MXenes are truly unique in several aspects. Not only you have so many ways of controlling their properties through selecting transition metal, X element, T surface terminations, mixing them in any way you want. So virtually infinite possibilities here. And changes are very big. Just one simple example, surface termination. You can have hydroxyl groups or oxygen. Surface terminations, hydroxyl, give you about 2 electron volt work function. Oxygen, 6 electron volt. Huge change, and you can tune it freely in between. And actually, you can change from oxygen to H by applying, for example, like a half a volt potential when you have monolayer of water molecule in between, because you will protonate, deprotonate the surface. And this is very, very unique. I mentioned to you several times that MXenes are metals, majority of them. So bare, all of them would be metallic. But what is interesting, the density of state is not as high as in gold or copper, which don't care when you do something to their surface and inject electrons. You can change it by changing surface termination. Like in this example, we can do it in situ. So we can actually modulate their properties, chemically and electrochemically or optically as well. So you have metals, but with properties that can be modulated, like in semiconductors. Our current entire electronics is using semiconductor for a simple reason. With applying small potential, we can change their properties, modulate properties. We can do this now in metallic materials like MXenes. And I think it again opens numerous new applications. And of course, they come in a variety of this complementing plasmonic color. You see, titanium 2C is red in solution, basically in transmission, and green in reflection. You add 1 layer of transition metal, titanium 3C2 now, and it becomes green in solution because its absorption band shifts from 550 to 780 nanometers. And you might be familiar with this, people claim, first example of human-made nanotechnology, where plasmonic, gold, and some silver nanoparticles in glass make this 4th century Roman cup, which is in British Museum, red in transmission, green in reflection. Last year, Nobel Prize in Chemistry went to inventors of quantum dots, and one of 3 guys, a Russian guy, received it for metal nanoparticles, plasmonic in glass. Exactly what actually Romans did quite a few centuries ago before him. But titanium 3C2 is exactly the same, and you can actually tune this color by changes of its chemistry or tune it electrochromically, green in reflection, red in transmission, with a difference. There is no gold here. This is just cheap titanium and carbon inside with oxygen termination. So we have all this array of properties that we can tune and control. Now, what do we do with these materials? I'm, I think, running out of time. I have like 20 minutes left, so let me show you a few things. First, we can very easily process them. So I mentioned already like a Dr. Blading. For example, this is my student produced by Dr. Blading, just spreading basically solution of MXene on the surface of film. And she's removing it from the polymer PVDF substrate. This film is 1 micrometer thin. It's 10 to 20 times thinner than aluminum foil, metal foil that people use. But it's highly conducting. Moreover, it has a strength exceeding strength of aluminum foil. Aluminum is between 150 and 500 megapascal. So you can make freestanding, very strong membranes, films, for variety of application. You cannot make process from metal to the same thickness easily here, and it's still highly conducting just after drying things here. And we know that, for example, like this paper airplane was published in 2014. It is still intact, sitting in my office, and this is like a 2 months old IFM film, remeasured in IFM, the same flake, and you see it really remains intact. So we can make this material sufficiently stable in air. This used to be a problem at earlier day of MXene research. So again, they are ready for many applications. And of course, we can assemble them with polymers and others and composites. And what you see also, these flakes are very straight. This is in PVA matrix. Because MXene, because of several layers, is much more bending rigidity, is orders of magnitude higher compared to graphene, which is flimsy, because it's very thin monolayer. These layers remain much thicker. And again, this is something that Eduardo has been doing, assembling polymers and 2D flakes long ago before, but now we have 2D flakes with drastically different properties here. And they have very good load transfer because of surface functionality, much stronger interacting with polymers, so you can have smaller flakes or small amount of material intercalating. This work with Ian Kinloch from Manchester, from Graphene Institute here. And people also start assembling them with other material. This is not our work. This is a work from Chinese Academy of Sciences, and Ray Bachman from UT Dallas published in Science like a couple of months ago. They combined MXene with graphene oxide, cross-linked by organic aromatic molecules to achieve pi bonding and electronic conductivity, reduced graphene oxide with HI, making RGO. This film, you see the same straight MXene flake, remember, has tensile strengths close to 2 gigapascal. Again, for people who don't know it, twice the strength of steel, good steel, quality steel, assembled at room temperature from 2D flakes and molecules. It's the future. It's basically something which allows us to take technology to the level which has not been seen before. Moreover, this film is also ionotronic. It conducts ion. They showed this film can work as a supercapacitor efficiently here. And basically, it just goes beyond everything has been demonstrated mechanically before. But again, remember, it's still conducting. It's close to like a 1.7, I think, 1,700 Siemens per centimeter. Still very good conductivity RGO and extremely strong canonical conductivity. Of course, this all opens huge opportunities for applications, which are very quickly shown about here. There are many, many of them. Again, like in the previous article, the 2023 count is not complete, so it's not decrease or slow down, but decrease here still shows that initial application energy storage, when we discovered MXene, as now still very big but not dominating film, sensors growing very quickly, textile, functional textile application, wearables, photocatalysis, electromagnetic interference shielding, but there are many others applications. And of course, if you delve into details for any other like sensors, it's everything from optical to electrochemical and strain and so on things here. So clearly enormous field to explore, and naturally this is something that you need specialists in each of those fields to use these materials. We provide building blocks. Now people who are developing new technologies need to use their expertise and knowledge to see how they can benefit from availability of all those new material things here. I can give just a couple of examples in the remaining side. In my group, we largely work on electrochemical energy storage. We're used to, Eduardo mentioned our work electrochemical capacitor. My still most cited paper was like a over 17,000 citation in materials for electrochemical capacitors, not on MXenes. But what is the goal there usually? The goal currently is to get devices which have high power, high energy, that can store energy faster than current batteries, that can store more energy than double-layer capacitors. How to achieve it? We need to do a few things. One, you cannot store much energy without redox reaction. Electrostatic storage won't give it to you. So we need materials redox active. Transition metal, niobium, moly, titanium, vanadium on the surface of MXenes are the ones that are used in many battery materials today. So you can do reversible redox. To get fast energy storage, you need to store it on the surface, like in activated carbon and other materials using electrochemical capacitors. In two-dimensional materials, everything happens on the surface. There is no solid-state diffusion. Whatever people do with solid-state batteries, they will never become fast energy storage devices simply because solid-state diffusion is fundamentally slower here. There are channels for transport of ions between the layers or on the surface. But there is one more thing that people rarely talk about. Conductivity. Titanium 3C2 has about 2 orders of magnitude to 3 orders of magnitude higher conductivity compared to porous activated carbon used electrochemical capacitors, the fastest energy storage devices. What happens if you have a poorly conducting materials and running a high current through it? Because fast charging means one simple thing. You simply run a very high current through a battery or capacitor or any other device. You get Joule heating. That's why your laptop can sometimes be really very hot when you put it on your lap. That's why car batteries have sophisticated, complex energy cooling systems. And when you have materials which have much higher conductivity, you can solve many problems. So it means that also much of the energy we produce using all means won't go wasted and hit the air and require cooling systems, but it can be used. So we believe there is a lot of application, but also remember this 10 times thinner than metal foil films of MXene. Imagine a current collector which is 10 times thinner and lighter. You can shrink the battery just by replacing current collector. And they're also separated right here. So we showed that we can have, for example, in protic electrolyte, redox reaction continuing up to 100 volts per second, or 100,000 millivolts actually. It's completely reversible to a supercapacitor rate, typical about 100 millivolt per second, but you still have redox, and you only lose maybe like a 40% of total energy storage, and this enormous rate, like a 5 to 10 millisecond charge discharge, and this is a reversible reduction of oxidation of titanium. Moreover, we were able to run titanium carbide supercap in sulfuric acid electrolyte to 500,000 cycles. This is at least an order of magnitude longer compared to other pseudo-capacitive redox active aqueous materials in here, and definitely it's only 8% loss, so we can certainly go to 1 million cycle what carbon inorganic electrolyte delivers. So it can be very, very stable things here. And I won't go further details, but we can, depending on the electrolyte and material, can go from purely intercalation chemistry like in a battery to double layer storage to intermediate this pseudo-capacitive storage things here. Can use other type of batteries. We can use it in metal sulfur batteries. We work with a company Giner on lithium sodium sulfur batteries, where MXenes can catalytically decompose polysulfide. They can prevent transport of polysulfide through materials. And again, sulfur has very low conductivity. It's dielectric basically here. Metallically conducting MXene in cathode can help to develop conductive scaffold for those batteries here. I already mentioned possibility of using current collectors, but what is important? Lithium grows parallel to the surface without forming dendrites, so we can work metal batteries, lithium, sodium, potassium, metal batteries. And we can use it also current collector on the cathode side, for example, with LFP, or as a conductive additive to NMC, LFP, silicon, carbon, for example, glassy carbon for sodium ion batteries, many other things here. And what is also very, very important, we all talk about flexible, printable devices, distributed electronic, Internet of Things. We can just put it from the ink, we can put it and print it on any surface. And those devices don't require current collector at all because they are simply conducting. So you don't have, and this has been always a major problem with making printable devices because people typically have to put a metal current collector, which is very difficult to deposit onto any surface because usually require vacuum electron beam or etching of metal foils. And here you just go and print it and let it working here. There are many other applications. Energy harvesting from solar batteries, electron transport layers, to ultrasonic electrokinetic salinity gradients. It's from review article a couple of years ago applications. I will show you just one example from our work with Korean collaborators on transpiration-driven electrokinetic power generation. So basically power generation as a result of water transport and evaporation from the surface. It was discovered by scientists at Wuhan University of Science Technology, Hozhong University of Science Technology in Wuhan, probably like less than a decade ago. And the main problem of this method was that the power was very low and energy amount low here. MXenes, because of its high conductivity, it just simply sodium chloride salt solution in water. You see, when orders of magnitude higher, this is a log scale. This is basically where we stand here. So we increase by a couple of order of magnitude compared to other materials. The performance, when it becomes practically, it's capable to generate practically useful amounts of energy. There are lots of activity on water desalination, ion separation, gas separation, membranes using similar principle, because you can do ion sieving, and through spacing between the layers, charge, and also applying potential, you can control transport of ions between things here. Very similarly, you have seen beautiful colors of MXene on a couple of slides before, complementing plasmonic colors of these materials here. And they actually strongly interact with electromagnetic waves from UV to microwaves and radio waves. And this leads to many applications, from light to heat conversion, from photothermal water desalination to cancer treatment, photothermal therapy, to antennas and EMI shielding here. This is just another example of combining metallic conductivity, transparency, and tunable work function. Work with Korea collaborator, Seoul National University, Teuli. They used MXene to replace ITO. Initial idea is simply they wanted to make LEDs bendable, and now they can also make them foldable and stretchable even with MXene. But because they were able to better match the work function compared to ITO, it not only prevented cracking when bent here, but luminance increased by an order of magnitude, so they became actually about an order of magnitude brighter compared to the same devices using traditional transparent conductor indium tin oxide, things here. EMI shielding. This was really the application that led, if you look at Google searches, to a spike in interest to MXene. All the devices, this pointer, cell phones that you use, computers, they need electromagnetic interference shielding, because otherwise there will be interference between all the communications. You can break your cell phone right now, and you will see metal cages around different parts of the cell phone, made of really pretty thick metal layers to make them freestanding here. Titanium 332 MXene appeared to line up with copper and aluminum in its ability to shield. But you remember I showed you this freestanding film you cannot make easily from metals. Micron thin. 50 decibel means like a 99.999% of small microwaves will be shielded. You can do it with 1 micron film. We can go to practically useful for many personal electronic devices, 99%, 20 decibel with 40 nanometer films today. This paper was published in 2016. Within 5 years, it became the most cited ever paper in the entire field of EMI shielding. And this is what I think is important. We need to look for properties where material outperforms all known materials and go after those application things here. And actually another paper with the same collaborators, Chen Min Ku, in 2020, we showed that titanium carbide, carbonitride MXene in a porous structure outperform at the same thickness even metals in their ability to shield. And we still don't understand completely the physics behind this. So there is lots of interesting physics to study. I kind of omitted it from my presentation today, but a lot of interesting stuff. But you take another MXene, vanadium carbide. This one reflect. This will be at very small addition, very successfully absorb electromagnetic waves when dispersed in materials, because it has very different dielectric properties, very different properties compared to titanium carbide MXenes. Same is with many, many others here. And I should probably wrap up within 5 minutes to keep it within an hour or less here. If you look at different MXenes, some of them, titanium 332, is, for example, has very low emissivity compared to polished metal, like gold. Some other niobium carbide are very good actually emitters, very good for space heaters, for example. They basically will emit heat. But what is interesting, this material is among the materials with the lowest emissivity, but it has thermal conductivity 3 orders of magnitude lower compared to gold. As a result, you can put on the surface of a hot plate, in this case heated to 80 degrees C, 200 nanometer printed. This is a logo of our university. And you see it remains cold. It remains pretty much at room temperature. This is 200 nanometer film. And we showed up to 400 degree temperature drop on micrometer thin films of MXene. Imagine all the building thermal insulation that is needed here. You can spray ultra thin film and prevent loss of heat in winter and excessive heating in summer. This can be very, very big here. And as you can see, again, the differences are very large, depends very strongly on the composition of MXene, and we can cover a very wide range. And this is an example, one of my students, Teng Zhang, wearing a t-shirt. So this was a white t-shirt. This is his thermal imaging picture in a cotton t-shirt. After that, we simply washed it in MXene colloidal solution. It becomes dark, scattering black, but you see now it does not emit heat, so it can keep him warm. And imagine with a sub-micrometer film, you can put it on any clothes, and this is definitely not the optimum way to put it, things here. And you can wear a silk blouse, go to North Pole, and stay warm. There are many, many other applications. Use your imagination again. Always think about properties. This is idea which was proposed by collaborators from Canada. I would never come to this idea myself because I simply didn't know such a need exists. It appeared that, well, it's kind of unknown. Like whenever you have microwave communication, like antennas and satellites, or your microwave oven, there is a waveguide that goes to the source to emitter antenna. And they're made of metal and need to be actually polished inside to nicely guide microwaves for communication with the earth. And they're both heavy metal devices and very difficult, expensive to machine because very often they need to have complex saying. This is one is twisted, this one is bent, and sometimes they need to go this way depending on the satellite design. Costing, if you can go to Google now, you will have from $500 to many thousands, and designer costs more. What they told us, we can make them lighter. They printed them antenna, making nylon. We again, just like this t-shirt, dip them into MXene, pulled out, dried. It's an order of magnitude lighter, more than a metal, but it actually performs at the level of metallic waveguides. And you can produce them at fraction of cost. So making them this way will cost about 100 times less compared to metal. And they try now to do like a thing of 3D printing. They can print them on Mars or somewhere else here. Now you can do it from polymer, which makes it lighter, same efficiency, and way cheaper because you really need just milligrams of MXene to coat it here. There are many applications. Gas sensors that can work at room temperature, be highly selective. Biomedical applications. People use them from photothermal therapy to implantable wearable electronics, epidermal electronics. And again, the idea is it's not more conducting than gold, but performance of electrode sensitivity depends on the impedance with skin and tissue. And because of these functional groups on MXene, it's a much lower. So you can get, for example, neural electrodes, implantable electrodes with much higher sensitivity, much more efficient signal transmission to tissue compared to commercial gold and platinum electrodes. So again, we can easily compete here. But there are many other applications going from immunomodulation to optical intraocular lenses, to antiviral, to sensing, and so on. And you see the number of papers increases very, very quickly in the field here. So this is basically my last technical slide. I want really you to start thinking different. Just like Steve Jobs suggested it, think different for Apple computer. We have materials with drastically different properties, but also enormous tunability of properties. They're available to you. You can make them using available recipe, or you can make new materials easily that have not been made before. They have a realm of applications that has hardly been explored so far. We're making first steps even with these thousands of papers a year already things here. And they can do just better in many applications as other materials. So if you're using something else, you may think, can MXene perform better? Just like these Canadian collaborators from University of British Columbia, who knew that there was a problem with, for example, waveguides, similar way you can print antennas, flexible antennas, so on. They knew that these materials can work for them. So similar way, whether you work on catalysis, electrocatalysis, developing structural materials, thermal management films or something else, you can think how you can use MXenes and go after this and many, many other applications here. There are actually books of MXenes, a couple of books you have seen covers an hour, but this book was edited by two of my former students, Chun Fan, John Zhang, and Michael Nagib, just published this month, brand new, has chapters written by top researchers in the field here. And we still are in the very, very beginning of the road. This was most exciting for scientists. It's not something that great has been explored. We are so great, we have done it all. You can all go home and be happy that problem has been solved. We're making first baby steps. About probably 0.1% of funding and effort that were invested into graphene have been invested into MXene so far. Properties that show to you in many cases already exciting. Those are properties on first samples, non-optimized, very far from what probably is achievable. Things here. So, but with so many materials, so many opportunities, it will take entire community to really take full advantage of this materials availability. So again, we made the first steps, but it's up to the community to take it from there and make breakthroughs in many, many different fields, discover new materials here. There are many physical properties predicted by DFT, not confirmed. Two-dimensional ferromagnetism, antiferromagnetism, chemically tunable. Chemically tunable superconductivity has already been demonstrated for niobium. Carbide, and depending on functional groups, they can be superconducting or not. Topological insulators have been predicted, again to be shown. Titanium fluorine terminated titanium 2C has been predicted to have cons, just like a graphene in the band structure, is still to be shown. So many other physical properties we need to understand or explain, for example, how this nanometer thin few micron white flakes interact with millimeter long microwaves, and so on. We still don't know which application will be the most important one. We can argue whether it will be shielding every piece of electronics, every building, every industrial apparatus for heat shielding, or it can be electromagnetic interference shielding of future flexible variable distributed electronics, or it may be catalysis in certain process, maybe more efficient ammonia synthesis, nitrogen binding, or something else we have not even imagined yet. And again, those opportunities here. But there is a growth, there is MXene gets kind of a similar attention to graphene. One of the reasons I'm here, I was in Madrid earlier last week, because I was invited to speak at the Graphene 2024 conference in the opening session. So it means that MXenes get pretty much clearly placed in the heart of community here. And there are many conferences. I came here from this EuroMXene Congress in Valencia, the first one in Europe. There will be a symposium on MXenes and the European MRS meeting in Warsaw in September. We will have our conference on August 5 to 7, and I have several flyers here, so feel free to grab one. Even if you cannot come in person, you can register and watch all the presentation online and learn much more about MXenes. And there will be 5th International Conference already in China, in Xi'an in October, and so on here. And this is my very last slide. Those really the people who do the job. This was taken just 2 weeks ago at the end of our quarter, a summer party at our place. This is a group of students, postdocs, visiting scientists coming from a dozen of different countries, very diverse people who really push the limits of knowledge. But even with this large group, we cannot do everything. We don't know everything. We collaborate with many people around the world, in the US, other countries, because there are great people everywhere who know much more than I do in many different fields. And of course, thank you for a variety of funding sources, including Wallenberg Initiative in Sweden, Murata company that licensed a couple of dozen of patents already from Drexel and filed many own patents. Federal funding sources in the US work closely with Carbon Ukraine, and who make max phases for us and also produce MXenes. And thank you for your attention. And maybe the very, very last thing here, I want to promote our non-orthography competition, which have been running for 8 years. We give up to $1,000 prizes. There are $10,000 in prize money. And any kind of micrographs, you produce something colorful, beautiful. I know you don't have color microscopes. Well, optical can do actually, especially polarized ones. But you can use Photoshop or any popular software. And you can become rich and famous. Not only having these pictures in our calendars, but many of them went to various type of postcards, book covers. This one was on the cover of Nature Protocols in June, latest issue, and so on. So again, we get pictures from many countries. There are pictures here among winners from Italy, Iran, pretty much anywhere. So feel free to submit your images. Just go online again and type non-orthography and you will find the website. And the deadline will be in September, so you have time to prepare your images. Thank you very much for listening to me.
Thank you very much. Thank you very much, Yury, for this excellent talk. And I have some time for questions. Please.
I know it was a long and exhaustive lecture. Probably went longer than I supposed to.
Thank you. I just wonder, how is the stability of the MXene phases when you are producing? Is this it's quite stable, or like a clay, or?
It really depends. Some of them are very stable. We tested, for example, films made of MXene, and this paper was published just like a month ago, 5 years ago. Some of them maintain exactly the same properties before. Some of them lost. And the idea was here that if you make them a film, if it's open structure, this one has tertiary amine as delaminating agents, which kept layers open to oxygen and water, and it lost its conductivity. This one was dried at elevated temperature slightly, it maintains conductivity. But this was previous generation of materials. Now we make titanium 332 films that we're pretty sure can stay in air for decades without degradation. But it depends on composition. Some MXene, like a thinner one, especially titanium 2C, V2C, are much less stable compared to, say, niobium 4C3 or titanium 4 N3 structures here. So many of them are sufficiently stable. All of them, we process them in air, in water, in the lab. None of them is processed like a glove box as vacuum. So compared to majority of materials used today, they're very stable. But there are limits. They can be transformed to oxide hydroxides. The transition metal carbides and nitrides. Thermodynamics is here. So we use kinetics to slow the process down.
Thank you for your nice talk. Yeah, I was wondering about what is known about toxicity and disposability of these materials.
As you see from a very large number of biomedical publications here, clearly for at least titanium carbide, niobium carbides, molycarbides, tantalum carbides, there have been quite extensive studies on cytotoxicity, blood compatibility. There have been some studies on environmental toxicity on zebrafish. MXenes so far have not shown signs of toxicity. However, keep in mind that the same variety of materials I mentioned to you will require much deeper understanding how the particle size, how surface terminations will affect this. Can hydrolysis of chlorine on the surface lead to toxicity, inflammatory response? Can soluble chromium or vanadium compounds from those MXenes cause toxicity? So again, you cannot talk universally about it. Those are materials. You need to study them here. But materials that have been used so far for biomedical application, primarily titanium carbides, niobium carbides for the thermal therapy, they have been, I would say, quite extensively studied, not showing signs of toxicity so far.
Regarding disposability, how is it to break apart these compounds if you want to?
Well, the same thing that is a problem sometimes with degradation is actually an advantage. You want to make them degrading. If you take titanium carbide, carbonitride, nitride MXenes, when they degrade in environment, they form titanium dioxide and carbon oxides or methane. I would say pretty much safe elements here. We can actually, and we have done it, design stability of material in demand. For example, people who use MXene for lenses want to have them stable over a long time in biological fluid environment. But people who use them for photothermal therapy or drug delivery don't want this particle to sit in the body forever. So what we can do, we can take the same MXene, but in one case make large flakes with very as perfect structures as we can make today for stability. But then we can make the same MXene with the same basically still absorption band, but with a lot of pinholes, defects, and non-stoichiometry and X lattice, which will degrade much, much faster. So, for example, killing cancer cells, it can afterward pretty quickly degrade and be removed from the body through liver and kidney as small titanium or niobium oxide nanoparticles.
Thank you.
More questions?
How big can be prepared the flakes?
So far, by solution processing, we know how to make flakes like larger quantities up to about 20 microns in lateral dimensions, which is again very big for solution processed materials. Single flakes we were able to make 40 to 50 microns, but you know, for single flake studies here. Fundamentally, there should be no limit. Also, people start learning for CVD. And let me just again take you back 15 years, 20 years back. Wafer scale graphene or continuous almost sheets of graphene on copper, this was something not appeared overnight. There were millions, probably tens of millions, if not hundreds of $1 million investment. People started with taking silicon carbide crystals, heating up at 1600 C, transforming monolayers into graphite, peeling off single graphenes to have larger crystals. After that, growing on nickel, and then copper method appeared here. Similar way with boron nitride, molybdensulfide, covering entire wafer here. Its all work is still to be done for MXene. So fundamentally, I don't think there should be a limit for this. They can potentially be grown by CVD on the surface. They can also be produced in larger flakes, maybe also assembled from organic molecules, like for example, it has been done from graphene on the surface, taking for example, metal organic compounds. But so far, we are talking about from microns to lower tens of microns flakes.
Okay, thank you very much again.
Mm-hmm.
Thank you.
Well, if you have further interest to MXene, just go to our website, very easy to find online. I think I have it somewhere here. And you will be able to find plenty of information about those materials. Again, thank you very much for listening, and hope some of you will get excited enough to start working on this subject. I know some of you are already working on it. Thank you.